Good morning, mathematicians. Welcome to Spectral Sequences, Part 1, where I'm going to teach myself spectral sequences. And I guess it's up to you if you want to come along for the ride. So, welcome to Spectral Sequences. Looking forward to it. We're going to start with the book, A User's Guide to Spectral Sequences, I think. And we will work our way out from there. Or maybe we'll stay there the whole time. It's like 600 pages. I don't know if I want to read the whole thing, but we'll see. We'll see. Holy guacamole, indeed. Ready for the roller coaster, yeah. Let's go. Let's get this book. User's Guide to Spectral Sequences. Spectral Sequence Saturday. Indeed. Okay, maybe I should download a hard copy here. Give me a moment. This PDF. Let's put it on my desktop. User's Guide to Spectral Sequences. Boom. Boom, boom, boom. Boom. Bing, pop, boom, pow. That's a reference to something. I wonder if anyone knows. Okay, we start here. Do we read the preface together? No. You guys can do that on your own. Oh, there's a quote here. It is now abundantly clear that the spectral sequence is one of the most fundamental algebraic structures needed for dealing with topological problems. You heard it here, folks. You heard it. Straight from Massey's PDF typed words. Boom. Part 1, algebra. I thought that would have been the whole book. Part 2, we don't even find out what a spectral sequence is until 23 pages later. He has 2.6 on Rate My Prof. Yeah. Well. Yeah, doing good math is not the same as teaching good math. I mean, not that Rate My Prof is an absolute thing. I don't know. Yeah, I don't know. McCleary has done a ton of homotopy theory. Yeah. And I'm sure he's written in this book. Oh, it does a lot in this book. Well, then we may not, I don't know if I'm going to go past 4. I mean, not that I'm not interested in homotopy theory, but I would like to do, I'd like to get to group theory, you know? In particular, here's one thing I'd like to better understand. Let me just show you guys. Let me see. Yes, this is the paper, I think. Is this the paper? It's about extensions of representations of p-adic groups. And I think somewhere here she quotes a spectral sequence argument. No, this is actually in... Gosh. I think she does mention it here, but... No, wait, what's the other paper? There's another paper that cites this paper that proves some theorems about extensions of representations of p-adic groups. And I just can't remember the name. Orlick. Orlick, that's the one. Orlick. Right, so a goal, there's probably a more direct route to this goal, TBH, but what would I personally like to accomplish from understanding spectral sequences? There is somewhere down here. Yeah, so I think this lemma. No, maybe there's a later one. That's just Frobenius reciprocity. But somewhere in here there's an application of a spectral sequence. And in part, I would like to understand why that is the case so that I may generalize the results of this paper. Weibel talks about Linden, Hochschild, Sayre for group cohomology. Okay. So we might go there next. But it's really just a special case of Leray-Sayre anyways. Okay. What do you need to know to get into this book? Basic homological algebra, presumably. Here it is. Proof of corollary 2. Yeah, there's some spectral sequence argument going on here. And I would like to understand it. And more. I would love to, there's many more things I would love to do with spectral sequences eventually. You'd like to learn chromatic homotopy theory one day. Was told if you know AG, algebraic geometry, it helps. Okay. Let's begin. Oh, you think you've got that down? Well then, great. I'm glad you're here. Do you want to hear the worst French accent you've ever heard in your life? Certains apaids joint ses calculs. Telles suivant moi la mission des géométries futures. I have no idea what I just said. Any good references for representation theory of units of maximal orders of division algebras over local fields? Unfortunately, I know nothing of that. Yeah. What's the link to the book? I mean, if you just Google it, there should just be a free PDF. You don't even have to go to some sketchy site. Maybe I'll link it in the description of all the videos. Okay. Well, I'm tired this morning, even though woke up late. I got finally put that paper out, and I just hit some deadlines for some job applications this week, so gonna try and take it easy this weekend. Okay, we're gonna consider the algebra of spectral sequences. However, we need to get familiar with the manipulation of these gadgets without the formidable issue of their origins. This chapter is something like a toolkit with computation techniques that may be employed by the user in the application of spectral sequences to algebraic and topological problems. Take a loosely axiomatic stance and follow from definitions. Okay, let's do it. Go get those 6 digits. A real short book would have 5 pages. Yeah. There is a spectral sequence. What is this non-constructivist nonsense? Let's begin with a basic goal. We want to compute H star, where H star is a graded R module or a graded K vector space or a graded K algebra or a graded is cohomology or it's homology. Take your pick. And we're going to have some helpful conditions, including that it is filtered. Okay, we're going to have a filtration. And two of those objects are intentionally left blank. Wait, I missed... What are we reading? We're reading a user's guide to spectral sequences. We are learning spectral sequences now and forever. And I mean, by forever, I mean probably for like a month until I get bored and need to take a break or feel like going back to class field theory. This book is a spectral sequence because it has pages. Exactly, Lockheed. You're gonna go places. You're gonna go places. For the sake of clarity, let's assume for this chapter that H is a graded vector space. And further that the zeroth piece of the... So link is, if you scroll up in chat, I did link it. But also if you just Google a user's guide to spectral sequences. That is, our filtration is bounded below... by H in the zeroth filtration. For example, if H... Oh, wait a second. That seems to be different. Then why did he do this notation up here where the increasing filtration seemed to be smaller? Whatever. I don't really even care anyways. Oh, no, that is the one that he wants. I see. Right, HN. Oh, no. Now I'm confused. It's a graded vector space. Oh, it's a graded vector space. We're going to say the gradings are all 0 below 0. Then there is an obvious filtration induced by... the grading. A less trivial filtration. To someone who works with cohomology, they are essential in the same way that the various integration techniques are essential to a student of calculus. First page already confused. What's confusing, Dason? Like, here's a graded vector space. Here's a graded vector space. Let's start a new thing. Spectral. His confusion will stabilize, yes. Well, we haven't proved that the confusion will stabilize yet. But let's take just a polynomial ring. And as a graded vector space, take the, it is isomorphic to sum of the degree D pieces, right? So it's C, direct sum, C times scalar multiples of X, direct sum, scalar multiples of X squared, ... And yeah, and then now a filtration. Maybe I'm gonna get the filtration backwards, but one way to have the filtration is that this will just be the whole ring, and then the second piece of the filtration will be basically the sum from D is 1. I'm going over graded vector spaces literally right now, Professor John Smith. And then the next one would just be, so you only take those terms here. And then the next part of the filtration would just be that you take only the degree 2 and higher terms, and so on and so forth. If you have some comfortability with singular cohomology, you'd recommend working out Leray-Sayre for the hop vibration. Well, we'll get there. I feel like we're many episodes away from that, but we will get there. Thanks for the suggestion. Do I need this for research? I don't know. I mean, a moment ago, right at the start of stream, I did point out a paper that I would like to understand that is related to my research, where they do quote a spectral sequence argument to prove something. And I am interested in understanding that proof and possibly generalizing it. Strictly speaking, is it directly relevant to my ongoing research projects? No, but you know, I just love learning. Yeah, they're not too important. So one other thing I should say about this filtration is, let's notice that our entire space modulo the F0 component is 0. If we go gotta think which way to do it. If we go F0, if we take the 0th piece of our filtration, I'm just going to write the F's instead of the graded vector space. If we take the 0th piece of our filtration and we mod out by the first piece of our filtration, we recover the complex numbers. So that was just the first graded piece. And if we take the next quotient in our filtration, I mean, what are we doing? We're killing off all this stuff. I mean, we just recover the pieces of the grading, right? We're just killing off the higher degree terms. So we recover this piece and so on and so forth. I love learning when the learning ends up in an NLab rabbit hole. You're somehow avoiding NLab in a very categorical rabbit hole. That's strange. That's weird. That's a glitch in the matrix. What's the philosophy behind filtrations? Could we have done that with any graded algebra? Yeah. I mean, let me tell you one thing about filtrations that that like I think is an interesting, useful thing. For example, well, okay, here's an example. I don't even have to go as fancy as indecomposable representations. Let's think about the short exact sequence of abelian groups, Z mod 2 into Z mod 4 into Z mod 2. We want to understand this algebraic structure, right? And we know that we can take normal subgroups and quotients, right? We know that we can take normal subgroups and quotients in order to sort of understand its pieces. So we take this group and we can take a filtration of that group, and actually we'll take a 3-term filtration, right? And the filtration that you take, well, we can always take more refined filtrations, but the point is the filtration at each step, right? So we know from writing this as a short exact sequence, we know that this is a group that is built out of 2 finite simple groups. And so if we take the quotients of each step of the successive filtration, right, we recover those simple composition factors, right? And this is useful because the thing is, the group Z mod 4 is not a direct sum of the group Z mod 2 and Z mod 2, right? It's somehow composed of these two things in a more intricate way. And yet, by taking this filtration, I mean, you think like the word filter, you're filtering stuff out. somehow it's sort of each step of the filtration, is filtering out some piece of it. And then by taking out quotients, we can sort of see, what is that simpler piece? So this thing itself may not be a direct sum of simple things, but we could always sum up. Oh, sorry, I wrote 0 here, but this is also a Z-mod too. Sorry, the 0 should have gone here. My apologies. But what we can always do, take a filtration and then sum up the quotients of the successive pieces of the filtration, and then we'll get this thing which isn't the original object, but it's some sort of approximation because we've summed up the simple bits that comprise it. Yeah, so hope that made some sense. So here's another example. If we have a CW complex, which is just some topological space built together by gluing more simple topological spaces, that has a certain kind of filtration in a sense. I mean, it's just a succession of subsets, but in particular, by the functorial nature of, we take cohomology, we get a map between each of these pieces, and we define a filtration to, say, be the kernel of this map. And then a filtration on here. Okay, yeah, that's just the end of the example. Abelian groups be the one place where division by 0 makes sense. Well, it also makes sense in groups more generally. And where else? I'm trying to think of other examples, but other examples are all technically just leveraged from the abelian group case. But groups would be the more general version. Yeah. So if we have a filtration F, this can be collapsed into another graded vector space. The associated graded vector space. So this is exactly exactly what I was talking about. Just read the first section. This is kind of complicated. Well, that's why I was trying to explain some of this stuff. That's why I was trying to explain some of this stuff. Yeah, wait, which way does he make the grading go, though? He makes, yeah, his F0 is the start. So this is exactly what I was talking about, though, with my Z-mod 4 example, was that if you have some filtration on a thing, you can sum up the quotients. So, and then that lets you see the sort of little pieces that build up your object. So what did he call this? EP0 of H is, see, I got to figure out a better writing system here. It's, okay, FPH modulo FP plus 1 H. And so the associated graded and then, yeah, in this case, our graded vector space can be recovered, right? Because this is just what? It's the sum. It's the sum over all of these, the nth piece, but the nth piece, by this construction, by the filtration that we were taking before, is exactly just this guy here. Which is what we were calling EN0. Oh, sorry, the sum of over all of these. Gosh. So EN0 H. You like to think of indecomposable objects as atoms? Yes. And non-trivial extensions between them as atomic bonds, making big molecules. That is nice, yeah. Certainly lots of people have said the thinking of simple objects as atoms, but I haven't heard anyone say that extensions are like bonds, but that tracks 100%. Applied cohomology, applications of cohomology theory to atomic physics. Well, Lockheed, if you stay with us, we may all come to an understanding of what the pages are calculating together. This sounds like parallelity map adjacent. I'm not sure. about parallelity maps, but parallelity map is indecomposable atom of a construction of segments with respect to an orientation of segments. Oh, right. I see. Is this you're the person? I'm so sorry, I'm blanking on your name. But we chatted recently about talking about counting orientations and things to do with the Sierpinski stuff. I'm sorry I haven't emailed you back. I've been all over the place. I don't think this is related to that. I don't think this is related to that at all, to be honest. But who knows? Name not needed. Well, Sawdust Creator. That's as good a name as any. You can interpret them language of R permanent cycles, right, and R eventual boundaries. Aha, I think we'll be getting there soon. If H star is an arbitrary graded module over some ring, however, there may be some extension problems reconstructing H star. Yes. As a simple example, consider the filtration induced by the grading. Here we have this. What? Yeah. Wait, what? Okay. I'm not sure I get what he's saying there, but because H star may not be easily computed, we can take as a first approximation to H star the associated graded vector space to some filtration. Yes, this is the target of a spectral sequence, right? So just like in the Zmod 4 video, the direct sum of Zmod 2 and Zmod 2 is not isomorphic to Zmod 4, but it's a first approximation to it. You'll dive into indecomposables and see if it fits what you're imagining. Well, sounds good. Will I be one of those professors that don't reply until one day before the exam? I don't think I'll be that bad. If my students message me on Discord, I usually answer sooner. We can take as a first approximation. Yeah. So we hope that H star can be reassembled from this. And so wait, did he call E star? He hasn't defined E star. I guess he just means. Oh, did he mean to call this E naught star of H star? I don't know. Before we give the definition, observe a simple property of the associated graded vector space to a filtered graded vector space. This thing is bigraded. Aha. Okay. So we can approximate cohomology with filtrations. Yes, that's exactly the idea. That's exactly the idea. I believe is that the thing is our cohomology groups might be complicated to compute, right? But maybe we can have some filtration and we can understand the successive quotients of those filtrations, and maybe from that we can build things up. Exactly like in this case. I mean, this is like part of the value of having a CW complex decomposition of your topological space. That's why he brought up that example, because yeah, we get a natural filtration on the cohomology coming from these simpler pieces of the CW complex, and that's easier to compute. And so the idea is that, well, we can make these simpler computations and compute the easier thing, the harder thing from these easier things. Okay, gonna try and do this terrible screen rearrangement here. It's not so bad. It's not so bad. But let's take some notes here, gang. Okay, so we are going to define the following thing. We're going to define Fp of HR is going to be the pth filtration of H intersected with the rth piece. And then we will define the 0th page of our spectral sequence, to be, holy moly, potato pudding and pie. It's Fp of H of P plus Q modulo F P plus 1 H P plus Q. Filtrations remind you of that naive class theory video that Preston O'Neill posted recently. I am not familiar. Can we take some limit or something? I think that's the idea. I mean, I think generally you want to cook up some filtration that collapses at some point. So the filtration has like finite length. I don't know if we absolutely need that assumption, but that is a helpful assumption to know that this process actually collapses. But yeah. So the index Q is called the complementary degree, and the index P is the filtration degree. And the associated graded vector space can be recovered as taking direct sums over index Q. To recover H directly as a vector space, we write that. So let me write that down. So HR, and let me write vec down here, will be the sum over P plus Q equal to R of E naught PQ. Okay, and what a great thing to end on. We will cover the first definition of a spectral sequence. So a spectral sequence is a sequence of differential bigraded vector spaces. So, in other words, you need examples to understand what's going on here. I think there will be examples soon. I mean, I think, yeah. Use this example of the polynomial ring. I gave the example of the polynomial ring. Definitely go back and work on go through this with the examples of the polynomial ring. Okay, maybe we can talk about maybe we can put in the polynomial ring example into here. So we'll do that in a second. Let's finish defining spectral sequence. So, and P and Q will be greater than 0. And then furthermore, we have a differential of by degree, of given by degree. So dr will take us from the pqth term of er to the p plus r q minus r plus 1th term. And that's it. So that is, oh, there's one other thing we want to say here. So, and then finally, we have that E R plus 1 So when he writes E double star, does he mean that this is he taking the sum over all of them? He means the entire graded thing, right? Like E double star means he's summing up over all of them. Is that correct? Is it? Can anyone fact check me in the comments here? If that's the biggest kernel image quotient you've ever seen, just wait till we get deeper into this series. No, he does not mean the sum over all of them. He means he means for each individual one. So let me write that down. So E. Well, I'll write down a more compact one. E r plus 1 of PQ is the kernel of dr modulo the image of dr. We call the R stage of such an object the ERth term, its ER page, and it may be pictured as a lattice. Boom. Bing, bop, boom. Yeah. Okay. We're almost subscripts are the same for both sides. Yeah. Is this the homology of pages? Yeah, it's basically that, I think. Oh, sorry. Hi, Poshek. You started reading Alufi. Nice. You don't study anymore, but you were always interested in math. Well, you can. That's a beautiful thing about math. It'll always be waiting for you when you're ready to come back to it. You hope you can understand some of the things I talk about in my videos. I hope so too. Yeah, this is part of your confusion with special sequences. Successive pages are cohomologies of the last one. So how is cohomology approximating cohomology? Well, I think that's kind of the point, is that as you go to successive pages, like, things become more or less complicated, and hopefully you can compute things in terms of simpler things. I mean, we haven't gone and proven this yet, right? So maybe once we prove these things, it'll make more sense. Something, take the limit of the indices and the arrows approach vertical lines. Something, yeah. Well, this is the introduction. Remember, this is all just supposed to be an overview. We're going to, in the second chapter, we go in and prove these things in detail. So, don't jump out, don't jump off yet if it doesn't quite make sense. Wait, thus, with this definition, consider this for r bigger than the maximum of either of those. Here the differentials become trivial since this, and that. Thus, these would be equal. Okay, And continuing in a similar fashion, this is true. Okay. What? Oh, for the maximum of these once it's bounded. I see. Okay. I see. So let me write that down. Let's go ERPQ has trivial dr for r bigger than the max of p and q plus 1. So ERPQ would be ER plus KPQ, and we call this the infinity page. Call this E infinity PQ. Okay, so I did say I would give an example of some of this stuff to someone who asked earlier. Pages is the index. Yes, exactly. Is like saying n sub. Well, yes, but this is true. But this is a very particular kind of sequence. This is not a sequence of numbers. This is a much more complicated object. There'd be no reason to call say the fourth term in a sequence the fourth page. But you're right. It's a sequence of just much more complicated things. So in that sense, it is similar. So yeah. Can you use a spectral sequence to compute cohomology of compact Lie groups? Probably. Probably, yeah. What course is this scene with only your trivial example? Prefer to play with baby toys first? I'm not sure if I understand the question. But let's look at our so let's go back to our example where well, I guess so what was it? So FP was basically we decided to call this the polynomials of degree at least P, right? And so let's go look at so FP HR, and so H, the R was exactly the polynomials of degree exactly R. And so this means then that for us, FP of CHR is what? That's FP intersect HR, right? So that's FP of CX intersect CR. And so, well, this will be there's two cases here. This will either be exactly the R degree polynomials when P is less than or equal to R, right? Because the FP part only sees, sorry, this should have been P. It only sees things that are degree at least P, and otherwise this will be too big and it won't see the degree R piece. And so, right. So then the E naught page, E naught PQ in this case. Good morning, Ken. So E naught PQ is the quotient of FP HP plus Q mod FP plus 1 FP plus 1 HPQ. And so I guess we have a few different cases here. based on whether so we have a few different cases here. Where the same tools I am using, but for examples like that short exact sequence, that you can think of generalizations and understand, go back to this. Well, this example I'm working out now, I guess, is an example. And FP, so yeah, again, we're going to have cases, but what did we need? So basically, if Q is at least 0, which we're always considering. So if Q is at least 0, then this will just be C P plus Q, I guess, modulo sorry, this is P plus Q. Modulo, and now let's see. So we need P plus 1 to be at least P plus Q. So there's two cases then. Either if Q is greater than 0, then it will just be this. But if Q is 0, then it will be this. And so we just get, it'll be 0 if Q is greater than 0, and it will just be Cx when Q is 0. And that's it. So I don't remember who asked for that example, but now you have an example that to go back and compute. And tomorrow we will come back to working through spectral sequences. So maybe I should have said this at the beginning, just as another example, just so you're aware. This first chapter there's all of this fancy talk, right? And there's all of these claims that we haven't proven, right? The point of the first chapter here is to just get you familiar with the working, right? So you're not supposed to understand these things right now, right? It's like how in engineering, or like in North America, calculus, we don't actually define a limit for you. We just sort of explain some rules, some abstract rules of integration, and we have you do some computations and get used to the minutia, like how to work with it, right? It's like how we teach you how to drive a car, most probably you learn how to drive a car before you learn how the car works. Most people don't learn how the car works. So chapter 1, we're learning how to drive the car. Chapter 2, we're going to learn, how to take apart an engine. Your confusion grows, or maybe you're asking too early, is this CX example what cohomology is the resulting spectral sequence approximating? That I don't know. But we will get there. Can we do filtrations twice or n times? I don't know what that would mean. But you could take a filtration. Is my analogy backwards? Are we taking apart the car first? You're not learning the inner workings of spectral sequences? Well, I wouldn't say I'm now. I mean, chapter 2, I did look over this a bit. Chapter 2 is where the inner workings begin. Here, there's some questions where he asks you to prove stuff, I think, without, where you're just supposed to accept some things without proof first. But anywho, that's yes, certainly you could take the filtration. You could, for each piece of a filtration, you could then filter those objects, I guess, in a different way. But that wouldn't really make a ton of sense because the filtration is already a decreasing sequence of objects. So, but I guess maybe you could filter it in a different way. I don't know. Does this have anything to do with chain complexes? Yes, this has everything to do with chain complexes. And we will get there in good time. But we'll have to continue with this tomorrow. I'll see you all then. And until then, oh, you just clicked this live? Well, sorry, sorry you came in right at the end. But all the recordings stay up on my channel, so you can watch the first part, and you can join us tomorrow for the second part. So I'll see y'all then. And